announcements. Homework 3 should be posted now. It was posted last lecture. And I posted just this afternoon the code demo we did in class off the webpage.
So I don't know, maybe I guess what's happening is that data that might not be available because there's like go to this website for the CSV or whatever.
Yeah, is the data not available?
It said like not, I don't know, it gave me like an error that was whatever.
Okay.
So that might not be posted.
Yeah, I thought I tested the links. Okay, so it I want to make sure I remember this at the end of the lecture instead of the beginning. So the link worked for me just now.
Okay. So
I just it could be if you copy and paste it, sometimes the tilde shows up as the wrong thing, but if you click on it, it should go to the right spot, and if not, correct the tilde is usually where the problem is.
Sounds good.
Yeah. So great. So it involves some stuff with regression and some stuff with gradient descent. And again, the last question is meant to be a little bit tricky. Okay. But you know, if you do something fairly naive and get something to show working, you'll get you'll get full credit for the problem, but you can do more if you try some more challenging stuff out. Yeah. So okay. So I also mentioned the Data Science Day is this Friday. I encourage you all to come if you can. There'll be some cool talks around campus and from companies and information on the new undergraduate program, and pizza at 11:30 as well. So if you go to datascience.edu and you can find more information. So quiz 2 came back. So Tia Locke has them, and we got Graham from. I thought he was going to be here. Hopefully, he'll be here after class to hand them back. Sorry, they weren't alphabetized last time, but the scores were pretty good. Okay, so we're going to start talking about gradient descent. Okay, and so this is basically the main algorithm used, or in some variation, to solve many problems in data mining and machine learning. So we started with linear regression because this is one you can do without anything like gradient descent. It has this nice kind of closed form solution, but just through kind of a matrix inverse in some way. But it's, in practice, it's usually solved using gradient descent instead. Okay, and we'll explain this. And so, especially in classification, we'll see towards the end of the semester. Again, gradient descent is the common way of solving it. So we'll start off with the different way, but we'll get to the gradient descent view of it as well. Okay, so to talk about, through this we have 3 lectures on this, and through this I'll talk about the algorithm and variants of it and how to apply it to kind of data modeling problems. But in order to really set the groundwork properly for this, we need to kind of start with some basics about functions. Okay, so you've probably seen a function before. We'll generally use a function, f for a function, and it's going to go from a domain of Rd in general, and it's going to go to a range of the real numbers. Okay, so you can define gradient descent and other problems over more complex scenarios than this. But this is what we'll talk about. This is what's most common and easiest to work with. It's the most common because it is the easiest to work with, but you can define this more generally if you want to. Okay, and so this means that will generally have a kind of a value alpha, which is going to be a vector in RD. So alpha will be alpha 1, alpha 2, alpha D. And so I'm using alpha. Often you'll see literature that's using X. I'm using alpha because one, it looks kind of like an X if you're far enough in the back. But two, it's often representing the actual parameters of some function that we're learning. So this is the parameters. This is the parameters of a model which we're learning, the same way as the coefficients in linear regression. Okay, so I use this for the coefficients in the model linear regression. That's the same alpha we're going to be using here. Okay, so for this lecture, it's just going to be an abstract vector. Okay, but in general, it's going to be kind of some model parameters. Okay, and the function will be determined by the data, and then we're going to optimize some function. Okay, so and the goal is basically, and I'll say this, I'll develop notation so I can say this more precisely over this lecture, but I want to optimize f of A, right? So f will be determined by some data we have. In general, we'll just write down some kind of example functions in class today, but we'll see how it will be determined by data. We want to optimize this function, and the optimum value is going to be the model we choose. Okay? And so before we had, the functions were special in some ways that we could snap our fingers and get a closed form solution for them, but in general that may not be the case. Okay. And so this will be kind of the basic premise. But I want to kind of define, kind of unwrap this what optimize means here, what optimum will mean, and this all. I want to do this properly so we have the right language to discuss more complex topics in this space. All right, so minima and so maxima. Okay, and so basically, I'm going to introduce some generality of functions to say, look, it could be like this, and then we're going to figure out a way so it's not like those bad cases. Okay, so we want to know what the hard cases are so we, in general, don't have to deal with them, and we can be sure we don't have to deal with them. Okay, so a local maxima of f is an alpha in RD, so in some neighborhood of alpha, let's call this neighborhood this, and I'll explain that. All other alpha in this, alpha prime in this neighborhood, have f of alpha prime going to be less than or equal. Okay, so this is local maximum. Yep.
So are these like functions like functions with like multiple variables?
Yes.
Or
yes.
Like single?
Right. So the way of thinking about this, and I'm going to draw pictures on the board here. Okay. So this domain, the y domain, is going to be the range of the function. This is one-dimensional. This is R. The domain of the function is going to be d-dimensional. Okay? Now, I can't draw in d dimensions, but for a lot of concepts, you can think of them as, okay, as such. So this will be the function f. Okay? And the function is a property that, maybe it's worth saying this, So I'll see over here, this notation here means every alpha in RD maps to some kind of f of some, say, value y, where y equals f of alpha. Okay, so basically for every point here, different color. All right, so I'm going to have some point here. This is alpha. It's a d-dimensional vector. Think of this as some d-dimensional space here. For every d-dimensional space, it's going to give me some function value f, which is here, right?
So then you think of it like, say, if d is equal to 3, that would mean you would have like 3 alpha values, and then you would like map that to a vector in R1 to a value of R1.
So which is just one value. Right, yeah. So now we can look at this picture, and yeah, so an example, a concrete example of a function might be f of, let's say, alpha 1, alpha 2, alpha 3. I can put 3 values in input, and this is equivalent to f of alpha, where alpha is a vector. And let's say this is going to be 2 alpha 1 plus 3 alpha 2 squared plus 4 alpha 1 times alpha 3. Okay, so if I put in a value, now I say alpha equals 1, 7, 2, then this is going to be 2 times 1 plus 3 times 7 squared plus 4 times 1 times 2, be 2 plus, give itself a harder one, 147 plus 8, which is equal to 157, right? Okay, so this is where our d, where d is equal to 3, right? So this is some function, happens to be a polynomial function. They don't need to be polynomial. In general, we'll have largely, until the last few lectures, we'll have polynomial functions, in fact. Yeah. Okay. Good. Yeah, so this is what sort of functions I'm talking about. Hopefully you've had calculus classes where you've looked at functions, multidimensional domain functions before. Okay. And we're going to need a little bit of calculus. Okay. But hopefully it's not hard calculus. Okay. It's just kind of notation issues. Okay. Okay. So okay, so in order to define this, I want to define some neighborhood. Okay, and so I want to say that this point here is going to be local maxima. Okay, and that means I can define some neighborhood down here where I map this point down here, and there's some neighborhood. This will be B of R alpha. Okay, so in general, what's going to happen is I'm going to think of this as now RD here, and if I have a point alpha, then I can think of a neighborhood. Generally, you could think of it like a ball. So this will be B of R alpha, and this will be a radius R. So this is a ball of radius R. It's all the points in RD within a distance R of A. It could be Euclidean distance. It could be some other distance. Would work just as well. Okay. Yeah.
So when we talk about the neighborhood, it doesn't really have fixed R, like it's just
right.
the vectors will be needed to be.
It just needs some neighborhood, so we can make R as small as we want, as long as it's positive. Right? So think of any positive radius ball is a sufficient definition of the neighborhood. Okay. So we say, and then I can define similarly. This similar definition gives me this is a local minima, right? So I can say a local minimum if this is going to be greater or equal than, right? So now I've got a local neighborhood defined here, and all the points in the neighborhood are greater or equal. Okay? And then if this is going to be okay, so so if I say f alpha alpha prime greater f alpha, and right, so this is not greater or equal than, this is strictly greater than, then I say this is strict. Okay? So an example instead might be, let's say the function was like this, and then it was absolutely flat here. Right? All these points here are local min. Every point along here is a local minimum, because there's a neighborhood where they're all greater or equal than this point, but some can be tied, right? So you can have a lot of non-strict local minimum. Okay? And when we're constructing functions with data, actually, there are going to be situations where we're going to have a lot of non-strict local minimum, but if we add enough data in the right way, it's going to be strict. Okay, so this distinction ends up being important. You actually get situations like this, where you have this entire subspace which will have the same value. Okay, and then we say that we have a global maximum of f if let's say is alpha in Rd if all alpha prime in Rd with alpha not equals to alpha prime have f of alpha prime less than or equal to f of alpha. Okay, so if all other values in Rd are less than this, all other alpha prime are less than f of alpha, then this is the global maximum. And similar, you can say global minimum, and you can make it strict if you remove this of equal than, turn the less than equal into just less than sign.
I was just going to ask if people talk about strict global maximums.
Yep, and this same thing will occur. We can get a situation like this with global minimum or global max that's not strict. Okay, and this will come up in understanding gradient descent. Okay, so there's lots of kind of terminology here. I'm trying to pick out the ones which are going to be relevant. Okay. Yeah, and so we're going to be okay, so I want to say we're going to be focusing on functions on so continuous functions. Okay, so the definition of continuous functions is like harder to write down precisely without opening a whole other so cans of worms. But we're going to assume that like say for all alpha prime, such that alpha minus alpha prime, say, is less than tau, then f of alpha minus f of alpha prime, then all right. So for all alpha in RD and some parameter delta, which is greater than 0, then there exists an alpha prime in some ball of radius r delta. So this is a radius that depends on delta of alpha. So some close point, then there exists, then for all within some radius, then f of alpha minus f of alpha prime is less than delta. Okay, so for any measure, for any point, any function value here, like this gives me some function value, and I can choose any kind of difference in the y value in the range delta. I say for however close I want them to be, then I can find a sufficiently small neighborhoods where all the function values are within this parameter. Okay, so this means they kind of eventually it's continuous. So I can have these weird. The first derivative doesn't need to be continuous, but the function needs to be continuous. So I can always it doesn't have jumps in it. Okay, if there are jumps in it, there are some technical issues. And anyways, we will be constructing these functions f so they have all these properties. Okay, so I'm just trying to state what the properties are, and then we will construct f so it has these nice properties. Yep.
So, how do you like decide whether or not to use like the minimum or maximum? Is that like based on the problem?
Depends whether you want to write a minus sign or not. So it's usually we usually talk about the minimum of functions, and we use gradient descent, which means we're going to go down towards the minimum. Sometimes we set up a cost function for our problem, our modeling problem, so you want to have a larger value, but then you say, well, the costs usually want to be small, so if that's the case, you take a negative sign. So like we wanted the maximum likelihood estimate. Right? Remember this was we wanted a maximum of something. But so we took the negative of the log, and that made it a nicer function, then we were minimizing it. So usually we'll talk about looking for the minimum of the function. But there's usually nothing inherently different than finding the maximum of the function. Sometimes there are things that you know about the function at 0, like it never is below 0, and then you want to say how close you are based on how close you are to 0 in some way, and then it's important to talk about the minimum when you're trying to quantify something, whereas the maximum makes it harder. It might be hard to do that. So in those cases, it might matter a little bit, but usually it does not matter. It's just a choice of the sign. Yeah. So very good question. Otherwise, you're like, no one tells you this unless you're listening. And you might be very well be wondering about this. Okay, so something else which is important are these. So saddle points. Okay, and in calculus, you probably learned about saddle points as looking something like this in one-dimensional functions. In high dimensions, we need to think about them slightly differently. Okay, So it's going to be some alpha in RD. So the local neighborhood, right? The local neighborhood around A has some alpha prime such that f of alpha prime is going to be greater than f of alpha, and some alpha some alpha double prime where this is going to be less than alpha, and you need another condition that the sets with alpha prime and with alpha double prime are not connected. Okay, so these points are not connected. Okay, so this is, I think, useful with an illustration like this one over here. Okay, so we're going to draw a space now looking down on the function. This is now the whole picture. We're looking down on RD. And I've got some point alpha here, and I draw some neighborhood around alpha. Okay? So, like before, if all the points in this neighborhood are other than alpha, are greater or equal than this point, then this is a local minimum. Right? But if it's a saddle point, it's going to be something like this, where I can decompose it into these regions where all of the points in here, this is going to be alpha prime. So f of alpha prime is going to, what did I say? It's going to be greater than f of alpha. And then all the other points here, this would be alpha double prime, where we're going to have alpha, f of alpha double prime is going to be less than f of alpha. Okay, and so, this saddle point comes from you have this, where we're out west, you have one of these horse saddles, right? And what's nice about the horse saddle, you're riding on the horse, is your feet can go down on either side, but the horse's head and its rump is behind you, and you can kind of balance them. Okay, so think of these are greater than, and so I'm riding on the horse, the head's off here, and my feet are going down either side, but I'm kind of can balance in the middle. Okay, but if you've ever been to a rodeo, sometimes it can be hard to stay on a horse. In general, I guess in general it should be easier, but the problem with the saddle point is that if I want to kind of walk down a function, which is what gradient descent is all going to be about, and I'm sitting right here, I can go down this direction or this direction, and they might go to different ways. If I fall off the left side or the right side of the horse, I'm going to wind up on a different side of the horse, I guess. So this is kind of a picture of like a saddle. Okay, and it doesn't need to have just two components. See, these are kind of not connected. This point is exactly alpha, so these are strictly greater than, less than. If it's, you might technically call it, if they're all equal, it might also be a saddle point. I don't remember the technicalities there. It's not so important. But you could have more than two of these connected components. Then you would often call it like a monkey saddle, and that's even harder to do. don't know why it's called a monkey set. You can use your imagination, which is usually fun with monkeys. Okay.
Not the way that we're drawing it here. It's not actually in the D dimension. It's just we're just thinking about it in like more like a 2 or 3 dimensional.
Yeah, so I've only drawn 2 dimensions, and then there's the Y dimension, which is coming out of the board and into the board, right? If you think of this being right on the board, right?
And this is just the help, like if there was some higher dimensions.
Yeah, so then, like in 2D, the neighborhood is going to be a disk, right? But in general, in 3D, it's a ball, or you call it a ball in D dimensions, sometimes a hyperball. But it's this higher dimensional ball around the point. So it's all the points in. So in general, you can define VR of alpha is equal to the set of alpha prime in RD, such that the distance between alpha and alpha prime is less than or equal to R. This is the closed ball. So this is defined generally in D dimensions.
Oh, okay.
Yeah. And so then if they're connected, like if there was a 3rd dimension and this actually is connected through here, then it's no longer a saddle point.
So in like the 3D case of a saddle point, in the worst case of kind of a gradient descent kind of algorithm, you have to check both like places where it goes down. Because like where else do you
Yeah, so what's known about functions with, we're going to try and avoid functions with saddle points for this class. It turns out that kind of the revolution around deep learning the last 5+ years has really been because we've gotten away from what we call from convex functions. And they've introduced functions with saddle points back into these. And so how do they deal with them? So the major concern is that you might land on a saddle point and then be like, maybe I should stop. And you're happy if you go either way. And as long as you keep going down, you're probably okay. It turns out. If you get to a local minimum, people are generally okay with that, as it turns out. But the more issues if you get stuck there and you don't know what to do. Then, and to realizing that you're at a saddle point and you haven't gotten all the way to the bottom. So that's usually the issue. You don't. So there are cases where it's important to explore all sides, and then this would be, I need to explore 2 sides. You know, it could be a picture where, let's see which one is, where it looks like this. And so it's still a saddle point, but the global minimum is over here. So I wind up here, and I can go either direction, and I get to the same spot, right? So this could happen too, and then I don't need to check both ways, right? So generally, you don't check both ways. Kind of, if you're in a situation where you're going to have all these branching points, and you think you need to check all possible directions, this starts sounding like an NP-hard sort of problem, like in the space of NP-complete problems. And those you generally don't want to deal with. You usually want to find something else to do instead of trying to do it that way. And so heuristics are usually used instead of trying to solve it to completion.
So I guess like this might just be in the realm of just like functions that are difficult. But like I don't know, I'm thinking of like a flat monotonic function, but then has like a moat around it with a local minimum somewhere outside that like diff moat. Is that another situation where it's just like
that sounds pretty hard? Yep.
Okay.
Yeah. It'd be good not to. Yeah. Nowadays, part of the machine learning process is designing an function f so that you can find a good local minimum in that function. If you're designing your function f so it has a plateau with a moat around it, you're probably doing something wrong. Unless you actually want to wind up on the plateau, or the story has gotten more complicated over the last 5 years or so. When I started thinking about putting together this class about 5 years ago, the landscape was, at least from what I thought it was a lot simpler. And anyways, but all these concepts are still useful in understanding what's going on nowadays. It's just you won't get it in this class. This is getting you ready for those cool classes. Okay. Okay. Good. The good news. The good news is that most, generally under some definition of most, brushing over all the measure theory here, most points are what's called regular points, okay, which is maybe you can guess from the name, and a regular point is an alpha in RD, such that some alpha in the neighborhood have f of alpha greater than f of alpha prime, and some this is less than f of alpha double prime here. So same as with the saddle point, but the regions are so connected. Okay, so that's going to look like here again. This is the space of RD, and then my point alpha like this, and then there's going to be all of these points here are going to have alpha prime with f of alpha prime greater than f of alpha, and these points down here, alpha double prime, are going to have f of alpha double prime less than f of alpha. Okay? And so most points on the function, unless it's some pretty weird function that we're not going to encounter in this class, are going to be these regular points where these points are below in one direction and the other direction they're above. Okay, and so most points will look like this, which is good. And we basically want, what we would like is that all the points look like this, unless they're going to be the global minimum. So either they're a regular point or they're a global minimum, and that would be nice. Okay. Okay, and the good news is we're going to construct functions which are generally that's the case. We're going to construct a larger family of functions. Where this is the case. Okay. Okay, so convex functions will be a larger class of functions, which is going to have the property that alpha of RD for f is going to either is going to be a regular point or the or it's going to be the global minimum. So there's only going to be one point which is not the is not a regular point, and this one is going to be not necessarily strict. So this could be more than one point. It might not be strict. Okay, and there could be other functions which are not convex, which also have this property. Okay, this is not just for There could be other functions which would be fine mainly for our purposes, but we'll be talking about convex functions. Okay, and as I mentioned, up until 5 or 10 years ago, all of kind of machine learning was basically trying to how kind of wild and powerful of convex functions can we build to model our problem. Okay, so in order to define convex functions, I need to first define a line L in, this is going to be a subset of RD. So it's going to be a line in RD, and I'm going to define it by 2 points, P and Q in RD. Okay, so L of PQ is going to be the set of points X okay, so a line is going to be defined this way in RD. Okay, so I think of the picture here. RD, you're going to have 2 points, P and Q. And so this is the line that goes through these 2 points. Straight line here. This is going to be L of PQ. Okay, and how do I interpret this gamma parameter? This is kind of useful to do. Lose my blue marker. Okay, as long as it's not behind that wall there. Okay, how many things have I lost behind the wall so far this semester? Just a pop quiz. I've been keeping track. 3 things. That's right. I think there have been. I think it's 2 markers and so 1 eraser. Okay, good. This might show up on the final. Okay, so we'll start with this. I want to show that P is actually on the line. P corresponds with lambda equals to 1, right? Because if I set lambda equal to 1, it's 1 plus P times 0 times Q. Okay, so that's just P. And again, if I do lambda equals to 0, I get Q back. Now lambda is 0, so this part goes away. 1 minus 0 is 1, and I have Q. Okay? If I set lambda right here, this is lambda equals to 0.5. 0.5. Basically, half of P and half of Q is the average of the 2 points. The average of the 2 points is right in between. Right? As I get to 0.75, it's here. 0.25 is here. Okay? So anywhere, and how about a point out here? How about this point, right here in particular? That's right. So this is lambda equals to -1. It's going to be -1 of P. 1 minus -1, that's going to be 2 of Q, right? So I'm basically getting yeah. So I'm getting 2 of Q, but then like minus P, and the way to think about it is I'm going to get Q plus Q minus P. That's what I did here, and that's Q, and Q minus P is going to be this vector. And I've moved it a distance of Q minus P to get out here. Okay, so I'm just doing vector calculus here. And I can describe all the points on a line in this way. Okay, so what's known as the convex combination of P and Q is in here. So this is the convex hull of the set P and Q. Is the region in between the two. Okay, and that's all the values. So the line segment between P and Q is if I restrict lambda to be between 0 and 1. Then this would be PQ, just the line segment. P and Q, just this thing. Okay. Okay, and so basically there are lots of ways to define a convex set. And one way of doing it is, so for any 2 points inside of a convex set, a convex set K in a subset of Rd if for all P, Q in K, then for all X in the, let's say, in the line segment between P and Q, X is also in K. Okay, so if I have a set here, if I have P and Q, then this line is entirely inside of this set K. Is this set I've drawn convex? The inside of this curve? No? Why not?
You can take like top 2 peaks.
Yeah. So I can put P and Q here, and then I can find some point which is outside. Right? So this says not convex. Convex is ensures that stuff is kind of round in some way. Okay. Okay, so this is for a convex set. This one is not convex, but like this set would be convex. A ball is going to be convex, right? Any of the LP balls we talked about are going to be convex sets. But like an LP ball with P greater or equal than 1, this LP ball with P equals 1/2 is not convex as it turns out. Right, so, okay, this is convex set. So, sorry, I like it. Well, we want a convex function, okay, which is slightly different. So, convex function f is that for all P and Q in Rd and lambda in 0, 1, okay, then we're going to have the property that f of lambda p minus 1 minus lambda q, right? So this is going to be less than or equal to lambda of f of p plus 1 minus gamma f of q. So let's draw function. This is going to be a convex function for now. So I illustrate what's going on here.
And that's lambda in the set, closed set, 0 to 1, closed interval.
Yeah. Open intervals works, gives you the same definition because
Yeah, just
the endpoints are P and Q, and this will hold.
Yeah, I just couldn't tell if that was a 1 or not.
Yeah, right. Yeah, oh, sorry. Yeah, that was pretty funky one. Okay. Okay, great. So this is our function f right here. Okay, now let's pick 2 points, P and Q. And go up to the function values. This is f of q. This is f of p. Okay, and then now, so I want to do this for all lambda. So I want to, let's start by thinking about this side here. Right, this side. What's the representation of this right-hand side here? For all lambdas between 0 and 1. I want to draw it in this picture.
There's a line that connects those 2 points.
Yep, it's the line segment between f of p, and q, f of q, right? Just so I have d plus 1-dimensional points, right? They have d coordinates plus 1 coordinate, and d, and so it's in d plus 1-dimensional space. It's just this line segment here, right? For lambda equals, this is lambda equals to 1/3. It's the point 1/3 of the way from p to q, right? And I get all of these points on the right-hand side. Okay? And now, if I look at the inside of this function, yep.
Is that all points on the function between P and Q?
Well, okay, these are the points these are the domain of the function, the input to it. So these are these points here. Inside the function, if I wrap it in the function, then it lifts it up here, right? So for all the points in between here, when I lift them up, it goes right onto the function, right? Okay. And so what I need to ensure is that the function values between here, right? So this corresponds with this point here is lambda p plus 1 minus lambda q for lambda equals 1/3. Right? It should be the same, this same point here. Okay, and the blue curve needs to always be below or equal to the green curve. I can't have it always below if it includes the endpoints. The endpoints are always exactly the same, but the function must be always below.
There's a difference between the domain part and the codomain part where there's lambda p minus, and then over here there's lambda p plus, or lambda f p plus. Are those supposed to be the same?
Oh, thank you. Yeah, it should be a plus. Thanks. Good. Okay, so this is for a fixed P and Q. I can draw the line segment, the green line segment between them, and the function must always be below that line segment. And for a convex function, this holds for all P and Q and all lambda. For all choices of P and Q, this choice, this choice, this choice, this has to hold. Okay, so let's look at some more examples. And this function is this function convex? Who thinks yes? Who thinks no? Who didn't raise their hand yet? Who still didn't raise their hand? Okay. All right. So of the people who voted, this is like the U.S. elections, like 40% of you voted, but you chose the right person. So congratulations, or the right answer. This is not convex because I can pick points P and, or say P and Q, and this line segment, right, the blue curve goes about here. Okay, it still may have a single global minimum. Every other point is a regular point, but it's not convex. Okay, let's draw some more examples. Well, this function. This one convex or not convex? This one is convex. Okay, because right, pick 2 points, P and Q. For any 2 points, the line segment between them, well, it's less than or equal. Right? So less than or equal, it turns out it's the same. So linear functions are convex functions. Okay, okay, good. About this function, this convex or not? It's convex, not convex. This, okay, you want a little more time to think? This one here, is this convex or not convex? This one?
I don't know which one is more.
This one is convex, okay? Even though it doesn't really, you can go off this way, maybe plateau, it doesn't need to have actually a well-defined global minimum, just like this one didn't. But for any 2 points, no matter where I pick them, this line segment stays above the line. Yeah.
Is it safe to map like our out to notion of like the second derivative onto like our understanding of convex concave? So like the first function, it would have had a positive second derivative at that one like point.
Yeah.
Right there.
Right, right.
And
in fact, it had a few, right, it looked like kind of like this. And so this whole, there's like 2 saddle points here and here, and this whole region, the derivative is the wrong way. Yeah. Yeah, so, so in 1 dimension, perfectly reasonable to do it that way. In higher dimensions, you can do it this way as well. We'll need to look at the gradient. I think the curl. Yeah, you may have to look at the Hessian to do it. I forget. Yeah. Okay, good. All right, so good. So okay, so convex functions have some nice properties. Right, so like we could kind of keep walking down, and even if it doesn't quite exactly plateau, we can keep kind of, water would keep flowing down here until this point here. And so this function would be okay to try and find the global optimum of, but it's not convex. So, but we'll stick with convex functions anyways. It's a nice abstraction. Yeah.
Sorry, I might have missed that, but you could isolate that as a convex function then. If
You can what?
You could isolate like a certain section of it as being convex.
Yeah, it's like, I mean, this part over this domain is convex, over this domain is convex, over any part of the domain that includes this, it's not convex. You might call it concave or something. I don't know. But that won't. We'll stick with convex functions for a variety of reasons. It'll be easier to state arguments of when gradient descent works with convex functions and certain types of convex functions that we'll define as well. So we'll specify further, and we'll. Okay. So we'll even restrict beyond this type of convex function. We want it to have well-defined gradient everywhere as well, and this one also has that. But these sort of things don't. It's hard to create a function without really knowing what's going on that might look like this, but is guaranteed to still be convex. Is kind of the issue, right? I can construct a function that looks like this out of data in some way, and it might be fine, but this might have come up a little bit too much, this bump, and now it's not convex, so now I'm stuck. Right? So we'll be kind of creating these from data using a formula, and if we use the formula the right way, we're going to know it's convex, no matter what the data looks like. And so functions that maybe could be derived that could look like this might also look like this, and then they're not convex. And knowing that would involve analyzing the function in a way that would be really expensive. So we want to kind of use kind of a formula that has properties that's going to guarantee it's going to be convex. And because we know it's convex, we know it's going to have like this property essentially. All right, yeah, so kind of the three properties of convex functions, okay, that are pretty cool, is that if f and g are convex, then say max of f and g, we can call this a function h. This is also convex. So I can do like a max procedure, which is pretty cool. These are convex. Then also h equals f plus g. Then this is convex. Okay? This will be really important because we're going to construct a bunch of simple functions f and g, which we know each individually are going to be convex, and then we're going to add them together. And we're going to know it's still going to be convex. This is part of this formula that I mentioned. And f is convex implies a no local minimum. Okay, so if that means, well, actually the if local minimum, I should say it this way, also global minimum. Okay, because a local minimum is a global minimum, so it doesn't have no local minimum, but if we find a point which is a local minimum point, based on some neighborhood property or based on the gradient, which we'll talk about next, we know it's a global minimum. We know we've reached a global minimum. Okay? So if we have a convex function, it's basically going to be, and it's going to have no local maximum or anything else like that, right? So we're going to use properties like this to construct a very complex function which we don't totally understand, but we'll be able to find its minimum. So that's kind of what's nice about convex functions. Where if I had things that look like here and I added some of these together, I might not have this guarantee. Okay. Good, so let's okay, and I may have alluded to this about 5 or 10 times already, but the gradient descent algorithm is basically we're going to start with some point kind of alpha here, and this is f of alpha, and we're going to decide somehow to take some step in some direction to some alpha prime, and we hope that the function value decreases if we take the step in the right way. And we're going to take the step by using the gradient of the function. Okay. So basically the gradient descent. Okay, the gradient descent algorithm, and I'll review this again next week, and we'll go into it in more detail. Better color. Alpha I is going to be alpha I minus 1 plus lambda times the what's called the gradient of f at alpha I minus 1. Okay, so with this is the gradient, and because I'm adding it to the vector in RD, this is going to be an element of RD. Okay, so I need to define what this gradient is, and we calculate the gradient, we multiply it by some factor, we add it to the current position, we get the next position, and we just keep doing this until we stop. Okay, so what is the gradient? Okay, so in order to define the gradient, we need to define of a function f, rd to r. We need to define the directional derivative. Okay, so the, yeah.
We're going up the gradient or going down the gradient? Like, should be a positive plus or minus?
Well, okay, so gamma was negative there.
Okay.
now gamma's positive.
Yeah.
Thank you. Yeah, good. Okay, so the directional derivative. So this is a multi-dimensional derivative. We have a domain of RD. Hopefully you've seen this before in a class, but if you haven't, you can define everything with directional derivatives, which I will do, which is still a one-dimensional derivative. You just need to remember that everything else everything else is going to be a constant. Okay, so I have alpha, which is an RD, and I have u, which is going to be in RD, and we'll say the norm of u is 1, although you don't really need to say that. And so then the directional derivative at u of f of alpha is going to be defined okay, so this is probably just like you've seen before for one-dimensional, this is RD, for one-dimensional values of alpha, except now we're doing with vector values, so we're applying it at d-dimensional values, but I'm adding some u, which is a unit vector, so it's a direction. All right, so I'm at alpha now, I'm in RD. I apply, so some direction u, right, and I multiply it by h, right? So if h is greater than 1, right, this could be hu, right? So now this point is alpha plus hu. Okay, and so as I shrink h, this vector becomes smaller and smaller, but it's a one-dimensional problem. I can restrict down to just this one-dimensional spacing. Okay. Okay, and we're going to be interested in functions where we're going to say f is differentiable if u of alpha is well defined for all alpha and u. Okay, so I'm taking a limit. I need to make sure the limit is well defined, and there's some details which comes with that. Okay. So it turns out directional derivatives don't have to be hard. Okay, what I'm going to do is I'm going to define a specific set basis vectors, E1, E2, up to ED, and these are all going to be in RD, where EI is going to be all zeros except the ith coordinate. So the ith coordinate is going to be 1, and everything else is 0. This is a unit vector. All right, so E of I, the norm of this is 1. Actually, it doesn't matter which norm I use here, but it's the 2 norm is 1. Okay? And so it turns out I really only need to define the directional derivatives with respect to these basis vectors. Okay? So then we'll say that, this symbol is, this symbol is, this thing is called a nabla. At some point I looked up the history of the name of that symbol. It's kind of strange, but okay. So this is an important notation. The directional derivative with respect to EI vector, we're just going to call this the directional with I here. So if I use I, it means it's referring to an index, which is a number, an integer between 1 and d. Otherwise, it's going to be a vector. Okay, and so, and this will be the partial derivative with alpha I. Recall that alpha is equal to alpha 1, alpha 2, alpha I, alpha d. Right? Okay, so this is the directional derivative, the partial derivative. So in order to do partial derivatives, I just need to say, well, alpha I is a variable. All the other values of all the other coordinates are going to be fixed. Okay? And so then it turns out that, and I'll go through an example, but let me just say that the derivative, which is a vector here, is going to be Okay, I'm going to take these partial derivatives. Each partial derivative is going to be a value, right? Okay, or it's a one-dimensional function. It's going to give me the range of it's going to be a function. But the gradient needs to be a d-dimensional vector. Okay, and so what I do, I take each of these values for each I, and I multiply them by this unit vector. And remember, this unit vector is all zeros except for 1, so it basically puts this in this coordinate. So this is going to be d of f, d alpha 1, comma, d of f, d alpha 2, d of f, d alpha d. Right, so it's just a vector here. And so each of these gives me one coordinate of this gradient. Okay, so we went a little bit quick here. Let me finish with a simple example of the gradient. And then, okay, so we're going to do alpha equals x, y, z in R3, right? And we'll look at the function alpha of x, y, z is going to be equal to 3 of x squared minus 2 of y cubed minus 2x e to the z. Okay? So now I can do d of f, d of x. Right, so this is just going to be 6x, this is 0, this is minus 2 e to the z, d of f, d of y, it's going to be negative 6y, right, and d of f, d of z is going to be negative 2x e to the z. Okay, so easy peasy. And the directional derivative, the gradient is going to be then 6x minus 2 e to the z, 6y, or minus 6y, minus 2x e to the z. And I can evaluate this at some function values, 3, minus 2, 1, which is going to be 12 minus 2 e. I guess again, not 12, 18. And minus 6e. Okay, so I can evaluate it at a value, right? So I need to evaluate this inside the algorithm. So I can calculate this function once, and then I just need to evaluate it here. Okay, and most of when we do this in this class, in a lot of cases, everything is going to be a polynomial. So you just need to be able to do, in order to compute the gradient, you just need to be able to take a partial derivative, which is just a regular derivative with everything else constant, with polynomials. Okay.
Sorry, might not just be seeing this. Where did the B come from?
The B.
Yeah.
Those are sixes.
Oh, okay.
Yeah.
Okay. That completely makes sense now.
That's 6. How do I write a 6 that's not a B?
For some reason, I think I just heard B, so.
Yeah.
Okay.
So to be or not to be. I'll leave you with that's your homework. So, all right, good. So I think we went through. This was pretty quick with the gradient, so we'll revisit this again on Monday next week, and then we'll dive a little bit deeper into the gradient descent algorithm and some of its variations. But so hopefully the stuff about functions was either pretty straightforward or you've kind of seen it before. It's just kind of terminology that you can ask for review if it comes up again, but I just want to get those proper definitions out. Okay, great. And if you're around on Friday, I suggest you come to the day science. I'll be pizza at 11:30. Oh, and quizzes. So the quizzes are up here, and they're in sort of order now. So that'll be. You log in sometime.
Thank you. Harmony, K. Tyler Adams at the top.
Yeah, so,
Sorry.
I didn't define what.
Sorry, what was it? Douglas Harmony with a K.
One thing you can.
Okay, better question. Why am I stressed? Why is this area?
Talk about the gradient, right?